Linear discriminant analysis. Linear discriminant analysis (LDA) is a supervised method for dimensionality reduction for classification problems. We start with the case where there are two classes, then generalize to k greater than two classes. Given samples from two classes C1 and C2, we want to find the direction, as defined by a vector W, such that when the data are projected onto W, the examples from the two classes are as well separated as possible. As we saw before, Z is equal to W transpose times X is the projection of X onto W, and thus is a dimensionality reduction from D to 1. Now M1 and M1 are the means of samples from C1 before and after projection, respectively. Note that the first M1 is in R to the D, and the next M1 is in R. We are given a sample X, which is equal to the set X to the T, R to the T, such that R to the T is equal to 1 if X to the T is in C1, and X to the T, R to the T is equal to 0 if X to the T is in C2. Now we let M1, the second M1, equals to the summations of the W transpose times X transpose times R transpose, summing for index T, divided by the summations of R to the transpose, summing for index T, which is equals to W transpose times the first M1. Now let the second M2, which is equals to the summations of W transpose times X transpose times 1 minus R to the T, summing for index T, divided by the summations of 1 minus R to the T summing for index T, which is equals to W transpose times the first M2. Now the scatter of samples from C1 and C2 after projection are S1 to the 2 is equals to the summations of W transpose times X to the T minus M1, then to the square, then times R to the T, summing for index T, and the scatter S2 to the 2 is equals to the summations of W transpose times X to the T minus M2 to the square, then times 1 minus R to the T, summing for index T. After projection, for the two classes to be well separated, we would like the means to be as far apart as possible and the examples of classes be scattered in as small a region as possible. So we want the absolute values of M1 minus M2 to be large and S1 to the square plus S2 to the square to be small. See figure 6.7. Fisher's linear discriminant is W that maximizes. J of W is equals to M1 minus M2 to the square divided by S1 to the square plus S2 to the square. Rewriting the numerator, we get that M1 minus M2 to the square is equals to W transpose times M1 minus W transpose times M2. Such a difference then to the square, if we expand it, it will becomes W transpose times M1 minus M2, then times again of M1 minus M2 to the transpose, then times W. So if we combine the M1 minus M2 times M1 minus M2 to the transpose, it becomes W transpose times SB times W, where SB is the between class scatter matrix. M1 minus M2 times M1 minus M2 to the transpose is the between class scatter matrix. The denominator is the sum of scatter of examples of classes around their means after the projection, and it can be rewritten as S1 to the square equals to the summations of W transpose times X transpose minus M1 to the square times R to the T, summing for index T, which is equals to the summations of W transpose times X transpose minus M1 times X transpose minus M1 to the transpose times W times R to the T, summing for index T, which is equals to, after we do the summation, there will be W transpose times S1 times W, and where S1 is equals to the summations of R to the transpose times X to the transpose minus M1 times X to the transpose minus M1 to the transpose. summing for index t, is the within class scatter matrix for C1 S1 divided by the summations of r to the t, summing for index t, is the estimator of sigma 1. Similarly, S2 to the square is equals to W transpose times capital S2 times W with capital S2 is defined as follows, is the summations of 1 minus r to the t times x to the t minus m2 times x2 minus x to the t minus m2 to the transpose, summing for index t, and we get that s1 to the square plus s2 to the square is equals to w transpose times sw times w, where sw is equals to s1 plus s2 is the total within class scatter. Note that s1 square plus s2 square divided by the total number of samples is the variance of the pooled data. Equation 6.33 can be rewritten as the following. J of w is equals to w transpose times sb times w divided by w transpose times sw times w, which is equals to the square of w transpose times m1 minus m2, then divided by w transpose times sw times w. And taking the derivative of j with respect to w and setting it equal to 0, we get w transpose times m1 minus m2 divided by w transpose times sw times w, then times the following terms is 2 times m1 minus m2. Then after that, we minus w transpose times m1 minus m2, then divided by w transpose times sw times w, then times sw, then times w. So after such a complicated formula, we get that it becomes 0, given that w transpose times m1 minus m2 divided by w transpose times sw times w is a constant. We have that w equals to c times sw to the inverse times m1 minus m2, where c is some constant. Because it is the direction that is important for us and not the magnitude, we can just take c equals to 1 and find w. Remember that when the probability of x conditioning on Ci is approximately by the normal distribution of mu I sigma, we have a linear discriminant where w is equals to sigma inverse of mu1 minus mu2, and we see that Fisher's linear discriminant is optimal if the classes are normally distributed. Under the same assumption, a threshold w0 can also be calculated to separate the two classes, but Fisher's linear discriminant can be used even when the classes are not normal. We have projected the samples from d dimensions to 1, and any classification method can be used afterward. In the case of k greater than 2 classes, we want to find the matrix W such that Z is equals to W transpose times X, where Z is k-dimensional and W is D by k. The within class scatter matrix for Ci is Si equals to the summations of Ri to the t times x to the t minus my times x to the t minus mi to the transpose, summing for index t, where Ri to the t is equals to 1 if x to the t is in Ci and 0 otherwise. The total within class scatter is Sw equals to the summations of Si, summing for index I starting from 1 to k. When there are k greater than 2 classes, the scatter of the means is calculated as how much they are scattered around the overall mean, that is n equals to 1 over k times the summations of mi, summing for index I starting from 1 to k. And the between class scatter matrix is Sb equals to the summations of ni times mi minus m times mi minus m to the transpose, summing for index I starting from 1 to k, with the ni is equals to the summations of ri to the k, ri to the t, summing for index t. The between class scatter matrix after projection is W transpose times SB times W, and the within class scatter matrix after projection is W transpose times SW times W. These are both K by K matrices. We want the first scatter to be large, that is, after the projection. In the new K-dimensional space, we want the class means to be as far apart from each other as possible. We want the second scatter to be small, that is, after the projection. We want samples from the same class to be as close to their mean as possible. For a scatter or a covariance matrix, a measure of spread is the determinant, remembering that the determinant is the product of eigenvalues and that an eigenvalue gives the variance along its eigenvector component. Thus, we are interested in the matrix W that maximizes. J of W is equals to the ratio between the absolute values of W transpose times SB times W divided by the absolute values of W transpose times SW times W. Now figure 6.8 is opt-digits data plotted in the space of the first two dimensions, found by LDA. Comparing this with figure 6.3, we see that LDA, as expected, leads to a better separation of classes than PCA. Even in this two-dimensional space, there are 9 altogether. We can discern separate clouds for different classes. The largest eigenvectors of SW inverse times SB are the solution. SB is the sum of K matrices of rank 1, namely mi minus m times mi minus m to the transpose, and only K minus 1 of them are independent. Therefore, SB has a maximum rank of K minus 1, and we take K equals to K minus 1. Thus, we define a new lower K minus 1 dimensional space where the discriminant is then to be constructed. See figure 6.8. Though LDA uses class separability as its goodness criterion, any classification method can be used in this new space for estimating the discriminants. We see that to be able to apply LDA, SW should be invertible. If this is not the case, we can first use PCA to get rid of singularity, and then apply LDA to its result. However, we should make sure that PCA does not reduce dimensionality so much that LDA does not have anything left to work on.